So let's take a look at an example that uses initial conditions. The example is I have a ball and it's thrown upward from initial height of 20 feet and it has initial velocity of 48 feet per second. Now I want to represent the position of the ball, which means the height of the ball, as a function of time. Now I was actually given two different initial conditions. I have the initial height, there's one of them, and I have the initial velocity, there's two. So initial height is equal to 20 feet. Well, my position function, if I represent it with s, which we commonly do, that means s of 0, the initial height. When I launch it, where am I? F of 0 is equal to 20. It also gave me initial velocity. That equals 48 feet per second. That means the velocity function, v of 0, which is the same as f prime or s prime of 0, because the first derivative position is velocity, must be equal to 48. Now think about what's going on here. Let's just say I've got this little building. This building happens to be 20 feet high. And I'm up here and I'm going to launch a ball. It's going to come up and it's going to go down. That's what's going on with this. So I start off 20 feet high and I launch it at 48 feet per second, and what goes up must come back down. So if we approximate the acceleration of gravity as 32 feet per second, then I have s prime of t, the velocity function, equals the antiderivative of the acceleration function. And the acceleration function is going to be negative 32 because the acceleration of gravity is negative 32. Negative because when I launch the ball, it's going up, and the acceleration is working in the opposite direction, going down, hence negative. Now, just as a quick reminder, s of t we think of as the position function. S prime of t equals v of t, which is velocity. S double prime of t, which equals v prime of t, which equals a of t, that's acceleration. Sorry, kind of ran out of room there. This is acceleration. So if I'm at acceleration, which is what I have, if I find the antiderivative, I'd be up here at velocity. If I then take the antiderivative of velocity, I'll be here at the position function. So the antiderivative here, notice there's no t, but actually there is, because this is actually the integral of negative 32 times t to the 0 dt. Remember, t to the 0 is going to be equal to 1, and there's actually a 1 there. I can put a 1 anytime I want to. So if I do like I normally do, add 1, divide by that amount, and then what do I get? I will get a negative 32 t plus c. So I know that s prime of t equals negative 32 t plus c. But before I can keep going, I need to figure out what this value of c is. But I know this is the position, the velocity function, and the initial velocity was 48. So if I set this equal, well, actually I should do it one more time. If I find s prime of 0, which is negative 32t plus c, and I know that is 48, we'll see that t right here is 0. So this is actually a 0. That's 0. That implies that c must be equal to 48. So s prime of t is actually negative 32t plus 48. But once again, we were asked for the position, and right now we're at velocity. So if I find the antiderivative of the velocity function, that would take me from velocity to position. So let's do that. I have s prime of t equals negative 32t plus 48. That would then mean that s of t equals the antiderivative of negative 32t plus 48 dt. Now when I find the antiderivative, see this has an exponent of 1, and in reality I have again a t to the 0 here. So I'm going to add 1 and divide by that, add 1, divide by that, and what I'm going to end up with here is this is going to be negative 32 t squared over 2 plus 48 t over 1 plus c. Well, this is going to cancel and give me 16. So I know my position function s of t equals a negative 16 t squared plus 48t plus c. But the problem is still that this is an infinite set of, or infinite family of vertical curves. So I need that initial condition. So let's go back and take a look here. And the initial condition says we start off at 20 feet. So s of 0 is 20. So I know that s of 0 equals negative 16 times 0 squared plus 48 times 0 plus c, and that equals 20 feet. Well, these are all 0, so that means that c must be equal to 20. So my position function, s of t, is going to be negative 16 t squared plus 48t plus 20. Now, this probably looks familiar because you've probably seen this a gazillion times in algebra. And in algebra, they did stuff like they said, like the position function, they may or may not have used s of t, they may have used like f of t, equals negative 16 t squared plus v naught t plus s naught, or maybe this was h. You've probably seen this formula in many ways, or many times, or in some format of this formula that you use in algebra again and again and again. It's very common to model, throwing a ball up and, figuring out when it hits the ground and that sort of a thing. Well, this is where it comes from. It comes from the whole idea of knowing the acceleration of gravity, finding an antiderivative, knowing some initial conditions, the initial height, initial velocity, and those initial heights, initial velocities end up in the equation. Right there is initial velocity, right there is initial height. So a lot of stuff that we use in algebra, and you saw in pre-calculus, are actually calculus results. So that's where that function actually came from. You used a calculus result that you can now just start from scratch and figure it out for yourself if you want to. So again, in terms of actually answering the question that was asked, I now have the position of the ball as a function of time. You tell me what t you want. I'm talking about this function right here now. You tell me what value of t you're interested in, and I'm going to tell you where you are. Notice that s of 0 really is 20, which is actually how we found that value right up here. So anyway, there's our function.